All right, 7.4, congruent triangles, ASA, AAS, and HL. We are still doing the exact same thing we did last section in 7.3, looking at two triangles, trying to prove them to be congruent, but doing that with a shortcut, basically seeing how little information can I know about these triangles and still prove them to be congruent. Last section we learned about side, 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 and side, angle, side. And this section we're just adding three more shortcuts: ASA, AAS, and HL. Okay, our first shortcut, ASA, angle, side, angle. As you can imagine or predict, it's a lot like side, angle, side. Basically, if two angles and the included side in one triangle are congruent to two angles and the included side in another triangle, then the two triangles are congruent. So let me show you. You have two triangles, and if all you know is that this angle and this angle are congruent to these two angles and their included side, remember it's important that the side goes in the middle. It's got to be ASA. The included side is also congruent. That's all you need to know. This proves that these two triangles are congruent. So you could say that triangle ABC is congruent to triangle XYZ. Again, this is ASA, ASA. Angle, side, angle. Our next theorem is angle, angle, side congruence theorem. By now you're probably catching on that the name has a lot to do with what we're looking for, right? So angle, angle, side. This one's actually interesting and maybe not one you would predict because it seems like it wouldn't work. But if I have two triangles and I have two congruent angles that you can see here, and I have a congruent side, this works. Now, but this is different than angle, side, angle, because the side, as you see in the title, is not included. It does not have to be in the angles for this to work. So you have two congruent angles and a congruent side anywhere. As long as you have matching and corresponding two congruent angles and one congruent side, the triangles must be congruent. It's just the way it works. Basically what's happening is, because three angles by themselves does not make any kind of size, right? So let me probably illustrate that better than I can say it. If I have a 60 triangle right here, I can make a bigger one that's 60, 60, 60 as well. So knowing angles doesn't determine the size of my shape at all. But if I just give it one length, just by giving it one length, kind of by locking it in these two triangles, determining that length, it does determine the size. And so my angles determine the shape, but by giving it one length, I guarantee that not only will my two triangles be the same shape, but they will also be the same size. So angle, angle, side, and the side does not need to be included. You're not really looking at these. And then this is enough to say that triangle ABC is congruent to triangle XYZ. All right, lastly, we have the hypotenuse leg congruence. This one's weird, and it probably already looks weird and sounds weird. It's just HL, no more S's or A's, just HL. So far, we've looked at theorems and postulates, or shortcuts, that work for any triangle. This only works for right triangles. Only for right triangles. And I hope you remember that a right triangle is basically any triangle with a 90-degree angle. And then the rule is simple. A right triangle, as you hopefully remember, has what's called a hypotenuse. Oh, I made that mark wrong. This is a hypotenuse. I just want to label this. It's also the word you see up in the top there. I know this is a bit crammed, but hypotenuse is basically the longest side, not the long side, but the longest side of a triangle. That's what we call it. And it's always opposite or diagonal from the right angle, the 90-degree angle. So as if you can just kind of look out that way and find the hypotenuse. So that's the hypotenuse right there, the longest side. And the way the rule works, if the hypotenuse and leg in one right triangle are congruent to the hypotenuse and leg in another right triangle, then the two triangles are congruent. So I'll illustrate that. Let me get a different color. So if the hypotenuse and one leg are congruent to the hypotenuse and another leg in two triangles, then those triangles are congruent. So hypotenuse, hypotenuse, leg, leg. These are called legs. I don't know if you remember that, but these are called legs right here. So the triangle has legs and a hypotenuse, and what you're looking for is the hypotenuse, hypotenuse, leg, leg, and this is already congruent, right? The right angle, if they're right angles, that means this angle is already congruent. So this is a lot like, you might maybe think of it as side angle, but it's called hypotenuse leg. You would write HL for your answers, and it only works for right triangles. This might be a little weird, but the reason this works is because this leg acts as like a swinging door. So if you can imagine this leg, if it could swing from this point up here, right? There's only one point, if this is a determined length, there's only one point at which it would actually meet and touch with this point right here. And so I know that's weird, but it's called like kind of the swinging door. That's why this rule works. There's only one time that this length of line would line up and actually complete and make a triangle. Otherwise, it's just kind of floating out here, or it's floating out here. So the swinging door, that's why this works, but you don't really need to worry about that. All you're looking for is a congruent hypotenuse, congruent leg, and of course the right angles are already congruent.